Welcome in, everyone. In this video, I'm going to go over the mean value theorem. First, I'm going to go over what it is, both in words and in pictures. You know, it's math, we've got to put our mathy words out there. Then I'll go over a couple examples of how the mean value theorem works. From there, I'm going to just spend a small amount of time going over Rolle's theorem, which is just a specific case of the mean value theorem. And then I have the word examples plural down here, but I'm just going to do one at the end of the video. Let's get into it. So what is the mean value theorem? The first thing that we're going to need in order to work with the mean value theorem is a function. So suppose we have y equals some function f of x. And suppose that function is continuous on the closed interval ab and differentiable on the open interval ab. Then there is at least one x value, which I'm going to call c, in the open interval ab, so f of b minus f of a over b minus a equals f prime of c. And this theorem, this is the mean value theorem, only tells us that there is the existence of some c value on the open interval to make this true. But what is this actually getting at? What this is getting at is, if you look down here on the graph, we have these two endpoints. So this is our interval AB. And I'm going to draw a graph between A and B that will be continuous, first of all, a function, and be differentiable on the open interval. And we have to call it differentiable on the open interval because you can't be a differentiable at a single point. So as long as I don't have any cusps or any corners in my graph, it should be just fine. So I'm going to go ahead and graph something like this. And what this equation is telling us is the following. This fraction on the left side is really just the slope formula in disguise. This is some y value, this is some y value, and the x values that are associated with them are right underneath. So it's the difference in y over the difference in x. So it is the slope. It is literally the slope of this line right here. Let's see if I can do this. There we go. It's the slope of that blue line in front of you. So how does that help? Well, what this equation is saying is the rate of change between A and B, the whole interval, will equal the instantaneous rate of change somewhere along the way, as long as you have a continuous differentiable function on that same interval. So that means that somewhere along the way, since I drew a graph that is both differentiable on open AB and continuous on closed AB, there are some points along the way, maybe like this one right here, and possibly this one right here, where the slopes of the tangent lines are also the same slope of the secant line. So something like that. And that's it. So again, you can only know that they exist. You need to use some algebra to figure out what the actual c values are, as you will see in the upcoming examples. I want to take just a couple minutes here to talk about the conditions of the mean value theorem. So the mean value theorem checks for continuity on the closed interval and differentiability on the open interval. So what that means is, if you take this function here on the left, I have the function and its derivative already worked out. We can tell just by setting each denominator equal to 0 that f is discontinuous at 0 and 3. So f being discontinuous at 0 and 3 means if there are any intervals that contain 0 or 3, then we cannot proceed with the mean value theorem. Meaning if we had possible interval like this, maybe 1 to 5, We would not be able to use the mean value theorem because the function would not be continuous on that interval. 3 is a discontinuity, and it is right in the middle of that. So maybe we try to find find an interval. How about we go from 1 to 2? Will that one work? So let's see, our only discontinuities are 0 and 3, neither of those are here. And the function is not differentiable on 0 to 0 or 3. So if we look at the open interval, is 0 or 3 in here? No. So we could use the closed interval 1 to 2. That would allow us to proceed with using the mean value theorem. We could also look at something like this. Maybe 4 to 109. Yeah, we could look at this interval. It wouldn't be very fun for calculations, but we could look at this interval for sure. Because this closed interval doesn't have any discontinuities, or rather we can say the function is continuous on this interval. And since f is not differentiable at 0 and 3, neither of those are in here, so this function is also differentiable on this interval, so this would be another one we could use. And we could come up with many others. But I want to take a look at a square root function. G of x equals the square root of 2 minus x. Now this function, since it's a square root function, is only continuous on its domain. So since we have a square root function, you know the domain is going to be restricted because we don't necessarily worry about imaginary numbers right now. So we can say g is continuous on its domain from negative infinity to 2. But if we look at the derivative, and maybe we can find out where the derivative isn't continuous, and you can probably pretty easily see it's not going to be continuous at 2 because that'll create a 0 in the denominator. We can go back and say that the original function is not differentiable. We can't find the derivative of this function when x equals 2. It's not defined. So we say the original function is not differentiable at 2. So it is differentiable on the open interval negative infinity to 2. So if we wanted to pick an interval here to use to make sure that the mean value theorem worked, we could pick any number, let's say negative 8 to 1, sure, that'll work. Because we already know it's going to be continuous from negative infinity to 2, this is just a piece of this interval. Great. We could, and if we look at the open interval, negative 8 to 1, that is also contained in here, so we're good. What if we decided to do something like this? How about 0 to 3? This one wouldn't make any sense because we can't substitute 3 into our original function without getting an imaginary number, so this one wouldn't make sense at all. But what if we tried to make an interval include 2? Let's say negative 19 to 2. Will this interval be allowed when we do the mean value theorem? And the answer is yes. Yes, this interval can be used because the function will still be continuous from negative 19 to 2. It's a closed bracket here. We include 2. But when we look at the open interval, negative 19 to 2, is it differentiable on this open interval? And again, yes, it is. We don't have to include the endpoint on the open interval, so we're good. We can use this interval and still be able to have the mean value theorem apply. Okay, the first example here, we are going to find c values so that this equation from the mean value theorem is true. So how do we do that? The first thing you need to do with every single mean value theorem question is first check the conditions. And we have 2 of them. And you can just simply write those out, right? F of x is continuous on the closed interval 1 to 4. And you can just cite the fact that f of x is a polynomial. Polynomials are continuous. The other one is not f prime of x, f of x is differentiable on the open interval 1 to 4. And that's because if you take the derivative of f of x, which we're going to have to do anyway, it will also be a polynomial, and that means that we're looking at a derivative that is continuous. If the derivative is not continuous, then the original function is not differentiable at some x value. So yes, the conditions are met, so we can go ahead and say the MVT tells us that there is a value c that will make this equation true. So from here, I think what needs to happen is you should find the slope of the secant line passing through these two x values. So some quick off-screen calculations will show that f of 4 is negative 2 and f of 1 is negative 11. Now that we have this, b being the second value in the interval over here and a being the first, we can just go ahead and write out this formula. F of b is negative 2 minus f of 1 is negative 11 all over b minus a. And we can go ahead and just figure that out. Let's see. That ends up being a 9 in the top and a 3 in the bottom, and that will equal 3. I would like to point out that this calculation will not always yield such a clean number, so just beware of that. The third thing we need to do here is find the derivative f prime of x, and that will equal 6x minus 12. Cool. All right. We just used the power rule for this up here. So then the last step here will be to set the derivative at c, which would be 6c minus 12, equal to 3, which we found up there. Right? F prime of c equals the slope of the endpoints of our interval, which we found right here. Yeah, then we just have to solve for c, and if you add 12 and divide by 6, you'll see that c equals 2.5 or 5 over 2 if you want to leave it as a fraction. And one thing I want to point out is that we did find this c that was guaranteed to us by the mean value theorem. Right? We could use the mean value theorem because of these conditions here being met. But even something else to think of, just to consider, is that the c value is on this interval or within this interval. In this example, we're going to do the same exact thing. We've got a piecewise function though, and I love this idea of having a piecewise function. So we have this piecewise function here, f of x equals this function when x is less than or equal to 3, and this function when x is greater than 3. I don't have an interval written down here, so let's go ahead and pick 1 to 5. Sure. We want to make sure this value is in our interval, and I'll explain why here in just a moment. The first things we're going to do is check our conditions. So one, let's see here. Is this function continuous? Well, this is a polynomial function. This is another polynomial function. On this interval, though, there's a break in the function domains right here at 3. So really what we have to do is we have to check that x squared minus 6x plus 14 equals negative 2x squared plus 12x minus 8 when x equals 3. And I just want to go ahead and say that it does. I believe both sides here will end up being 5. Yeah, that looks right. So yes, this is continuous on the open interval 1 to 5, but we also have to check for differentiability at x equals 3, because again, that is where the break is. So let's check that second condition. The derivative of the top part, or the top function, is 2x minus 6 equals the derivative of the bottom function is negative 4x plus 12. And we need to check that these are equal when x equals 3 again, because that's where the break is. So let's check it here really quick. Let's see. The left side will be 0 when you substitute 3 in for x, and the right side will be 0. So we can say the original function is differentiable on the open interval 1 to 5. And again, we only had to check this point because if they're polynomials, the derivatives will also be polynomials. So the derivatives are continuous, which means between 3 and 1, this is differentiable, and between 3 and 5, this is differentiable. We just had to check this one value. So from here, we can just go ahead and start substituting our values in for x, of course, in the correct function. So if we're going to find f of 1 here, this will be using the top function. And so we'll just substitute 1 in for every x value in the top function to get 9. F of 5, on the other hand, will use the bottom function. So we'll have a negative 2 times 5 squared plus 12 times 5 minus 8 equals 2. Hate it when my pen runs out of ink. All right, I'm going to continue this example on the next slide. I would suggest you write f of 1 equaling 9 and f of 5 equaling 2 down, just for reference on the next slide. From here, we just need to go ahead and set it up. We need f of b, which is 2. We need f of a, which is 9, all over b minus a. From here, then you can just do some simplification. It's negative 7 over 4, and that's it. That's what we got for the slope of the secant line from 1 to 5. The next step, of course, is to find the derivative of the function. But since this is a piecewise function, we would have to find the derivative of each piece. So the derivative of the top function from the previous slide would be 2x minus 6, and again, that would be from x less than or equal to 3. And the derivative of the bottom piece is negative 4x plus 12, for x being greater than 3. What does this mean? Well, we have to check for anywhere the top piece at c, not x, we have to check out where the top piece is equal to negative 7 over 4, as well as where the bottom piece is equal to negative 7 over 4. So here are the two separate functions set up equal to negative 7 over 4, which is the slope that we were looking for. And we just have to solve for c in each case. And I will release those steps slowly. So here are the answers for each of these separate functions. Now, one last thing, and while I can say yes for certain that this is one of our answers and this is one of our answers, we really just have to go back through and double check a couple things. Really what we're doing here in finding these answers are finding some unknown x values. And considering the interval that we were looking at being 1 to 5, the first thing I want to do is just make sure, are these numbers in this interval? Well, I don't know what 17 over 8 is off the top of my head, so I used the calculator to see 2.125. Yeah, this number is in this interval. And also the same thing here, 55 over 16, I had no idea what that was, so I used the calculator, and yes, this number is in this interval. Great. That doesn't mean that they both work. In addition to being in this interval, we also have to make sure that they fit within this interval. So we can only use the top function for numbers x values between 1 and 3. So since we use the top function here, is this number between 1 and 3? Yes. So we can count this as one of our answers. And the similar idea with this bottom function. We can only use numbers that are greater than 3, but not bigger than 5. They have to be less than or equal to 5. Does this number fit in there? Bigger than 3? Yep, because we use the bottom function. And it's less than 5? Yeah. So both of these answers work. You just had to do a little bit of extra checking to make sure that these answers fit within these intervals and this interval. Let's say you take a thermometer from a freezer to check the temperature of your boiling water. You know, normal everyday human stuff. The temperature rises from -5 degrees Celsius to 100 degrees Celsius in 14 seconds. And what you're going to do is you're going to show the temperature was rising at 7.5 degrees Celsius per second, somewhere along that rise from -5 degrees Celsius to 100 degrees Celsius. The way to think about this is the following. We know that the temperature was changing with respect to time, and it took 14 seconds to change. So what that allows us to do then is say that the temperature is the dependent variable, and the time is the independent variable. And then what that allows us to do is say, make some ordered pairs here, right? Independent you can think of as x, dependent you can think of as y. And at 0 seconds, right, from when we took that thermometer and instantly put it in a pot of boiling water, still trying to get over the fact that that is a normal human thing. Otherwise, why would it be in a math book, you ask? Yeah. So we can create some ordered pairs. At 0 seconds, the temperature was -5 degrees Celsius. Likewise, in 14 seconds, at the very end, it was 100 degrees Celsius. So we can find that f of b minus f of a over b minus a we have done in all of the other examples. So f of b, the later time, the function value would have been 100 degrees Celsius minus a -5 degrees Celsius, which would have been f of a. B minus a would have been 14 minus 0, aka 14 seconds. So we would end up here with 105 over 14, which is 7.5 degrees Celsius per second, if we have the units there. Now, the sort of natural mathematical part to this is that, well, is this function continuous, the function of time and how the temperature changes with respect to that? And the answer is yes. Like, the temperature just doesn't jump from -5 degrees Celsius to 10 degrees Celsius to 35 degrees Celsius and so on. It changes continuously between these two values. So yeah, we're looking at a continuous function, and there aren't any cusps or corners that you could think of, which would be like the temperature stops increasing just for a split second, only to keep increasing again thereafter. So this function of temperature changing with respect to time is also differentiable on the open interval from 0 to 14. So the mean value theorem definitely works here. And what the mean value theorem says is the rate of change over the entire interval will equal the instantaneous rate of change somewhere along the way. So yeah, the mean value theorem works. And because of that, since this is the rate of change over the entire interval, the instantaneous rate of change somewhere along the way between 0 and 14 seconds had to be 7.5 degrees Celsius. So what is Rolle's theorem then? Rolle's theorem is just a very specific case of the mean value theorem, and you'll see that it looks very, very similar to the mean value theorem as we go through the actual theorem. It starts out the same way. Suppose you have a function y equaling f of x, and that function is continuous on the closed interval ab, differentiable on the open interval ab. And we have this new condition here that f of a equals f of b. And the only thing that does different is it makes this the endpoints of our interval at the same y value. So if we meet all three of these conditions, then there's at least one x value, again I'm going to call c, in that open interval ab, so f prime of c equals 0. And that's the other difference. In this original version of the mean value theorem, there's this really awesome fraction that is f of b minus f of a all over b minus a. But since we put this in here, that f of a equals f of b, in this numerator, since this will equal this, we're subtracting the same number from itself, which is just 0. And 0 over b minus a is going to be 0. That's why we have a 0 on the right side of the equation. And really, how that helps is that will help us find possible maximum and minimum values a little bit later on. 0 sloped tangent lines line up with maxes and mins. So yeah, that'll be helpful in a little bit. Let's take a look at an example of applying Rolle's theorem. So here we're going to use Rolle's theorem, but first, of course, like we did with the mean value theorem, we have to check the conditions. So 1 and 2, I can definitely say f is continuous on the closed interval -3 to 1. It's a polynomial, which means it's also differentiable on the open interval -3 to 1. The third thing that you have to check then is what is f of -3 and what is f of 1. So you can come along and just substitute -1 in for x everywhere here and -3 in for x everywhere here and crunch those numbers, and I promise you this time it's going to be 0. So 0 will be our solution here for both of these, and they match. And that makes me as a math professor happy, because that means you can go on and show me how good your algebra skills are. I love that. We have one calculus step, right? I've got to take the derivative of this at c. So I'm just going to take the derivative of this normally and then replace all of the x's with c's, like this right here. From here, we can go ahead and solve this equation, right? We're going to take that derivative at c and set it equal to 0. And this ends up being the rest of the problem, right? There was that one calculus step, everything else is algebra related. So we've got this quadratic. Fortunately, it factors, so that's not going to be, 3c and c. This will be a +5, and this will be a -1. So we can set each of these equal to 0 and solve for c. So c equals -5 over 3, and c will also equal 1. Okay, so now we just have to check to make sure these are on the interval. So -5/3 is in this interval, but oddly enough, this is one of the endpoints of our interval. If you go back and look at the after the conditions for both the mean value theorem and Rolle's theorem, we will find C values in the open interval AB. This is what it says in both. So the open interval AB here would be -3 to 1, which we've already looked at back here. But this one is not in the open interval. We cannot include it in our answer. So in this case, the only one we will have is -5/3. I hope this video helps you out. Good luck.